For this example, we're going to use the properties of logarithms to condense the following expressions as much as possible, if we can, down to one term. The common logarithm of 50 plus the common logarithm of 2, the common logarithm of 2 minus x minus 2 times the common logarithm of x, 3 times the natural logarithm of x plus 1/2 times the natural logarithm of x plus 5. So here we're going to make like water on the outside of a cold glass and condensate. For our first example there, for number 1, we have the common logarithm, log 50, plus the common logarithm of 2. So, we just pull them together using the reverse direction of the product rule. So this becomes the common logarithm of 50 times 2, or the common logarithm of 100. And then remember, common logarithm is defined as log base 10. So that's log base 10 of 10 squared. Or, depending on how you want to think about it, either the product rule done once with a condensation, or the power rule done once, or that old rule we talked about in the last section. However you want to see that, you should recognize that the answer there is 2. And this is definitely a way you can see that this is good, because log base 10 of 50 is not a nice number. Well, yeah, it's not actually that bad. And log base 10 of 2 definitely isn't that nice of a number. But 2? That's a lot more reasonable. Might be why you'd care. And then for our second example, we're dealing with something a bit more variable, as it were. Well, if you want to deal with the common logarithm of 2 minus x, and this is a case where I'd probably recommend using parentheses just so you know it is the common logarithm of the quantity 2 minus x and not the common logarithm of 2 minus the quantity x separately. Anyway, you got that minus 2 times the common logarithm of x. Well, what I would start by doing here is pull that 2 to the inside. So you'd have log of 2 minus x minus log of x squared, and then just liberally apply the quotient rule. So you get 2 minus x over x squared. And that's how you'd condense it down. I don't know why I was clunky about saying that, but that's what you do. Then finally, for our third case, we would have in there, for that 3 natural log of x plus 1/2, I don't know why I wrote the parenthesis there, it's just an old habit, of the natural logarithm of x plus 5. Again, I'd recommend throwing the power rule in first, whether you'd like to or not, that's up to you, I guess. But here, I like getting my logarithms as matched up as possible first. So, we would have in there the natural logarithm of x cubed plus the natural logarithm of x plus 5 to the 1/2, or hopefully you know what that 1/2 power is going to turn into in a second, but I wrote it that way just to be sure. And again, you should be really careful here when you're thinking about this stuff, that like you don't say, oh, okay, I'm just going to add these two parts together because I got a logarithm on the outside, and that logarithm's like the inverse of the distributive property, right? Not exactly. Remember that we're dealing with things in terms of exponents, not explicitly, but implicitly. I was about to say explicit, but it's not true. So a lot of those types of algebraic things, like if this was a y times x cubed and a y times x plus 5 to the 1/2, you'd pull them together. No, not quite. You gotta be a little bit more careful here. It's a little bit more subtle. You gotta think a little bit more exponentially to get these relationships down. Anyway, here, got these two. We have the same logarithm, so we use the product rule, and we get that this can be written as the natural logarithm of x cubed times the square root of x plus 5. Or I suppose if you really wanted to here, you could make this x to the 6th and bring it underneath the radical. I personally wouldn't do that, but hey, maybe. Although you should also be wary of doing things like that, especially with these two examples here, because these connections might change the overall behavior if we're treating this as a function. It might change what options we have. It might change the domain just a little bit, in the same way that canceling out terms from a rational, where you have common factors, it does add some values. So does doing this sort of thing here. Well, In this case, it might subtract some values, might change some values. Just be mindful of that when we're doing this algebra, that there could be a little bit going on underneath the surface that we're going to ignore just a tiny bit at the moment while we're still picking up the pieces. Anyway, this is how you can use our rules here to pull things apart, take them together. So the last thing we're going to see for this section is a very special formula that allows us to put anything we want to in terms of these two most important logarithms. We're going to look at the change of base formula.